Hi, I'm Mike Morrow, and I'm a automotive technology instructor for a couple community colleges out here in Southern California. I teach at the Joshua Tree campus, Copper Mountain, and I also teach at College of the Desert in Palm Desert, California. I like to teach the higher technical stuff, electrical, electronics, different things like that. So today I'm doing a video on pulse width modulation. I'm doing a simulation on a bench. It's actual working pulse width modulation, and show you how, hopefully kind of explain how that works and how they can use it for different things, controlling motors, lights, servo applications. So I'll get started here in a minute. So I'm going to show you some of the tools I'm using for this this video. I got a laptop, of course. I recommend, because of all the stuff that we got, picoscopes and oscilloscopes, different applications we can plug into our laptops, that you have a pretty good laptop. I recommend gaming laptops. Gives me an excuse to play games too. But anyway, gaming laptops have a lot of power. They have good graphics. This one has 3 USB ports, plus it also has a USB-C high-speed port where I can plug multiple things into just that single port. I'm also using a picoscope, which is pretty well known in the automotive field. It's a 4-channel scope. I can plug in 4 different connectors and check 4 things at one time. I have my breadboard that I use for little projects for testing different components and stuff like that. And I have a Fluke voltmeter, which is also connected into my PC right here in the right-hand lower corner. It takes a little USB adapter. I really don't like it. I wish they could connect this through the Bluetooth, because I can connect that. That's their FC Fluke Connect series. I can connect to my cell phone via Bluetooth with no problem. Trying to connect through this little Wi-Fi connector sometimes is a little bit of a hassle. So, Fluke instrument. I got a power supply here, a bench power supply. Got it set at 12.6 volts. And in my breadboard, I'm going to zoom in here on this so you can see what's going on here. But I got Fluke currently running right now here on the lower right, and then Pico's running on the left here. Pico runs on your computer also. Okay, so I got a close-in shot here of the microprocessor, the evaluation board I'm using, and this is actually an Arduino Nano Every. This is their newest miniature microprocessor evaluation board. I'm going to use that because I can generate a pulse width modulation signal easily with it. Actually, I can generate 6 of them if I need to, which is what they use in a lot for robotics. Here's a dime just to kind of show you how small this thing is. And the microprocessor is right here. And that has 48 connections on it, believe it or not. And these processors here are for USB. This connects to a PC. I can program it through a PC. I can see what's going on with this microprocessor through a PC. So if you want to control anything in the outside world, the output on these things are only about 20 milliamps, 20 thousandths of an amp. So that's when we get into, we look at this unit here. This is a driver, and this driver connects to the microprocessor. This driver can handle about 10 to 15 amps. It's transistorized, and the Arduino sends commands to it to whatever we want to do. If we're doing pulse width, it just amplifies that pulse width. I have it connected to, let's back out here. I have it connected to 12 volts. So on my power supply. And that's the other thing. The Nano only puts out about 3 volts. So I couldn't run any automotive applications with that. I need my 12 volts to run my lamps and motors and things like that. So, and while we're here, I'm going to go ahead and show you that it is actually already connected. I'm getting a 5 volt power supply from my PC. I have 12 volts here. I'm not connected to anything 12 volts, but I do have an LED on the board there. And let me turn this light out. And you can see you can see on the screen, my volts went up. My voltmeter is showing about 1.4 volts. And then we also have a pulse here. And this is what this is all about, pulse width modulation. I'm going to show you the signal. So this is one pulse. So I got a pulse of about 3.5 volts for so many millionths of a second, and then it's ground, and then it pulses again with the same width of the pulse. And see, what's changing is that width. The wider that pulse is, the more voltage there is to whatever you're connected to. So you see my LED getting brighter. You see my voltage going, my average voltage. So if I go all the way over, it's going to be about 3.2 volts coming out of that circuit. So to be able to control this, I'm using a variable resistor potentiometer, and it's built into the program to be able to read what this potentiometer is doing. So I can control the light, how dim or how bright I want that LED. LED only pulls about 5 to 10 milliamps, so this board can easily control that. But if I want to hook up to an automotive light bulb, then I'm going to need to use my driver. So that's what we're going to do next. So the pulse width modulation, I hope I explained it good enough. And again, the pulses between the two lines is 1,000 times a second. So 1,000 times a second, it's sending this small DC pulse out, and then it converts back down to negative, then goes back up to positive. And when we get about halfway, that we consider this the duty cycle. So that's about a 50% duty cycle, which is about right. I got 1.5 volts on my voltmeter, and my bulb's fairly bright now. It'll go brighter. So that's pulse width modulation, and we can control lights, motors, and servos, and we're going to show you examples of everything here. So we get out of the screen real quick. Okay, off to the right, I have a 1157 bulb here. This is an automotive bulb. Used to be real common. It's a dual filament bulb. It has one filament that's not real bright, and that's used for normally like your tail lights or marker lights. And then there's one element that gets really bright, and they use that for turn signals and brakes. That used to be very common, and now everything's going to LED. So I'm going to show you. I can control now that I'm using the driver. I got the 12.6 volts going through the driver, and I also hooked up my voltmeter, my multimeter, to the power coming out of this driver. So you'll see that now. I left the signal coming out of the microprocessor the same, so you're only going to see that 3.5 volts coming out of there. I notice when I tie it to the high side, I get a lot of distortion, so I'm just going to leave it this way so it's a little clearer to see what's going on. So you can see my very narrow pulse there, maybe 10% pulse, and I get about 0.5 volt going to that bulb. It's glowing a little bit, so you can see on the screen 0.5 volt and a very narrow pulse. And if you can read over here, I'm pulling about 1/10 of an amp. So as we ramp this up, let's go about 50%. See that bulb starts getting really bright. I'm pulling about 1 amp now. I could never do that with that microprocessor. That's why I need this driver here. Okay. And that's about right, about 5.1 volts. So if we crank this all the way up, the bulb gets to its total brightness. I get about almost 12 volts, and I'm pulling 2 amps now. That bulb pulls quite a few amps. So again, that's all going through this driver, not through the microprocessor. So that's how that pulls. So this is how we can control some lights on cars. Some of the things I've seen is the dome lights that have that dim out on you. Your dash lights controls used to all be done with resistors, but now they're starting to use pulse width modulation. So let's go to the next step. Okay, what we have in this demonstration is right over here. I have a squirrel cage blower motor that's from the inside of the car. This is what circulates the air inside your car for your air conditioning, heating, your defrosters, your fresh air, air recirculation, whatever. That's a 12 volt motor. Same thing. So it's 12 volt DC motor, so I can control the speed of that motor with pulse width modulation. So we're going to show you this example of this. Same circuit, nothing's changed. I didn't change the program, anything. Same thing I used to control that light bulb. So I got about 1 volt. I can see that motor's moving pretty slow. You can see my amperage is a little higher though, 1.3 amps. That's a pretty good sized motor on there. So that, my pulse width about 30%. Let's go up about 75%. I'm pulling 3.5 amps. I don't know if you can hear that motor, but it's blowing quite a bit faster. I'm getting about 6.6 volts to it on the average, and I can feel the air blowing off of it. And I can crank that all the way up. And I don't want to leave it too long because I don't trust this little driver to handle that kind of amps. That amps was clear up to, I think it'll go up to about 8 amps. That little motor pulls. So again, I'm pulling 8 amps through this little driver, and I can feel it's warm. But the microcontroller is just still spilling out the very few milliamps it needs to control that driver. So that's how we control the speed of a motor, and it's just not blower motors. There's other motors on the car that can be controlled, like window regulators, door locks. Some door locks have almost like a motor in them to pull the lock out of place. Different applications. So let's go on to the next demo. This is what controls the speed of the engine. There's a big butterfly valve in here. This goes right on top of the engine, and we open and close that valve, that butterfly, to allow more air or less air into the engine. This is what controls the air into the engine, which also controls how fast the engine speed or how much horsepower we need. These used to be controlled by cables and linkage, and then before these we had a carburetor, which also had linkage and cables. This is fully electronic. It's controlled by the ECM and by the position that we have, which would be our throttle pedal here. And so I'm going to show you that example. So there's full electronics inside this thing that receives that pulse width, and it knows as that pulse width gets wider to start opening that throttle. So I'm hoping we can see this. I think we can see it from there. So let's go ahead and open it up. You see that throttle opening on the right there. You see my voltage going up, my pulse width getting wider. So as that pulse width gets wider, that throttle responds to it. I want to go halfway, want to go all the way, just widen that pulse. So that's how that works. So this works with pulse width modulation. Same signal I used to control the blower motor and the light bulb. I didn't change anything. So, and you saw the voltage go up also. This won't take a full 5. I think this only goes up to about 5 volts on this this particular system. So that's that. Okay, so the last part of my project, just so you guys think they're not out there saying, well, he's using Arduinos and he's using resistors, and what does this have to do with cars? Okay, I admit the Arduino is not a car computer, but it's a microprocessor. It's actually a professional microprocessor, and I forgot to bring up the data sheet. It has a 100-page data sheet on it. Those processors aren't built for Arduino. They're built for industrial and commercial applications, and Arduino just takes them and puts them on their evaluation board. So what I've done here is I still got my throttle body here. I replaced the potentiometer with an actual throttle pedal off of a car. Okay, these are all off of different, I think this is off of a 2014 Ford Focus. The throttle body's off a 2007 5.4 V8. That's why it's got that big bore in it like that. And that blower motor, I believe, was out of some kind of a Chevy Impala or something. Kind of showing you, we don't have a lot of variations in the actual electronics of it. The variations is the shape of it, how it mounts. I don't know if I could put this on a Chevy Impala. I'd probably have to drill some holes and I could probably make it work. But anyway, what this is, the throttle pedals originally were, a lot of them still use these potentiometers. The same thing. A lot of times they have 2 in there and sometimes 3. They have redundancy in case one fails. you still have a throttle, okay? And you're going to get a check engine light and tell you, hey, you need to fix this out before the other potentiometer goes out. This potentiometer actually is converting the voltage. It's internally. It takes a positive, negative, and it sends out a varied voltage without. So it probably has the potentiometers built into it, is what I'm thinking, without me tearing into the circuit. So I'm just going to show you the demo. I'm going to push on the throttle, and as you can see, I get the same result. You can see my pulse width getting wider. See my voltage going up. And you see my throttle opening and closing. So that's how it works, guys. This is what we call, if it was an aircraft, we would be calling it fly-by-wire. That's what that means, is when they eliminated cables and mechanical connections and went to all wire. So the only thing that connects my foot to my throttle is electrical wire. So that's just the way it is. That's the way it's gone, and it's gone. You started seeing these fully electronic units coming out, I believe, around in 2005, where they eliminated the cable completely. So to sum it up, this is pretty much it. I wanted just to try to show you how pulse width works, what it's used for. So we saw it used with the lamp, we saw it with the blower motor, and we also saw it actually controls the throttle of our car. There's other applications where it controls the little door valves, or the little doors inside your HVAC system, where it switches from defrost to the blow in your face, or to heat and cold. That's all now starting to be controlled by pulse width modulation type servos. Used to be cables, and then they went to vacuum, and now you're starting to see servo applications with pulse width modulation. There's a lot of pulse width modulation used throughout the car now. And it's a big list, so I don't want to go through it. Especially today's cars are fully electronic. So anyway, that was my demonstration. I hope you guys enjoyed that. I have several other videos I've put together, and I will continue as I'm teaching. So you have a good one.